This video will cover a solution guide to problem 46 from Chapter 5. A small car with mass 0.8 kilograms travels at constant speed on the inside of a track that is a vertical circle with radius 5 meters. If the normal force exerted by the track on the car when it is at the top of the track is 6 newtons, what is the normal force on the car when it is at the bottom? The strategy here will be to draw free body diagrams for the car at the top and the bottom of the loop. From these diagrams, we will be able to write out their Newton's second law equations. Using those equations and the information given to us in the problem, we will find an expression for normal force at the bottom of the loop in terms of known variables. At the top of the loop, the car experiences two forces, the normal force from the track and gravity. Because the car is on the inner part of the loop, the normal force from the track will push the car down towards the center. Gravity will also be pulling the car down towards the center. At this point on the track, the centripetal acceleration, which is always directed towards the center, will be pointing in the same direction as the two forces. If we allow the downward direction to be the positive y direction, we find that the normal force added to the gravitational force is equal to the mass of the car times the centripetal acceleration. At the bottom of the loop, the car will experience the same two types of forces. However, because the track is now below the car, the normal force will push the car upwards while gravity will still be pulling the car down. Again, the centripetal acceleration is pointing directly towards the center, so, allowing the upward direction to be the positive y direction, we find that the gravitational force subtracted from the normal force is equal to the mass of the car times the centripetal acceleration. We are now at a point where we need to look at the equations we've derived and the information we've been given and try to come up with a plan to find an expression for the normal force at the bottom of the track. The problem gives us the mass of the car, the radius of the track, and the normal force at the top of the track. If we look at the equation for the car at the top of the track, the only information we are missing is the centripetal acceleration. Looking at the equation for the bottom of the track, we are missing the normal force and the centripetal acceleration. Because the car is moving at a constant speed, and centripetal acceleration is defined as the square of the velocity of the object in motion divided by the radius of curvature, we know that the centripetal acceleration is also constant. We can use this information and substitute the expression for the centripetal force from the top equation into the equation for the bottom. Doing this, we find that the normal force at the bottom is equal to the normal force at the top plus 2 times the gravitational force. Subbing in the values for these variables, we find that the normal force at the bottom is equal to 21.7 newtons upwards towards the center of the circle. What becomes clear from solving the problem this way is that the car's apparent weight, or the normal force at the bottom of the track, is over 2 times its actual weight. In order for the car to continue moving at a constant speed around the track, the normal force has to be greater at the bottom since the gravitational force is no longer in the direction of the acceleration. This would cause a passenger in the car to feel much heavier than they are at the bottom of the track than they would at the top.